Welcome back to the second half of this lecture about radiation and how it's going to be part of climate. Now, there are a lot of aspects of our climate system that are about radiation. How radiation is being reflected, how it's being absorbed, how it's being transmitted. Whether we're talking about ice sheets or greenhouse gases or the ozone layer or the atmosphere or clouds, there are a lot of factors in a lot of climate processes in our climate system that are about how radiation is moving through. For example, ice sheets. Ice sheets have a very high albedo. Remember, albedo is about the fraction of visible light that is being reflected. Ice sheets are bright white. They have a high albedo. They reflect most of the incident radiation that hits them. Well, incident shortwave radiation anyway. We don't yet have a good sense of what they're doing with longwave radiation. Let me give you a hint about that. In general, reflection and longwave radiation are two words that don't very often go together. Most objects, be they the surface of the Earth, greenhouse gases, the atmosphere, clouds, whatever, in general, reflecting longwave radiation doesn't happen. Okay? In general, don't think in terms of reflecting longwave radiation. But, we got other things in the climate system that are awfully high in albedo. I mean, look at this cloud deck. This is a deck of stratocumulus clouds as seen from the International Space Station. Well, look at this big old bright white layer of clouds here. Tons of shortwave radiation that is from the sun that is incident on the top of this big old layer of stratocumulus clouds is getting reflected back up into space and never hit the surface of the Earth, never was incident upon the surface of the Earth. It never even had a chance to warm the surface of the Earth up. Clouds play an incredibly important role in climate. We're going to have to figure that out if we're going to be able to figure out the energy balance of the Earth and why temperatures are changing and so on. Now, it's not terribly hard to see how ice sheets play a role in this. They reflect short radiation, same with clouds. By the way, remember back in the paleoclimate lecture where we talked about snowball Earth? You can see how snowball Earth was a real problem, right? Once most of the Earth was covered with ice sheets and sea ice, almost all the radiation from the sun was being reflected away from the surface of the Earth, keeping the planet cold. Once the planet became pretty much covered with ice, it was actually a very difficult problem for the climate system to come up with a way to get rid of all that ice, because most of the ice most of the surface of the Earth was covered with ice. It was reflecting most of the radiation away. In fact, it's an active source of research right now in the climate sciences to figure out how did we get rid of the snowball Earth situation. I'll give you a hint though, it probably involved greenhouse gases. There probably were changes in the Earth's atmosphere that added more greenhouse gases, and the greenhouse gases made the planet warmer. Oh, I'm giving away a secret. Okay, so it's not hard to picture how ice sheets or clouds are reflecting radiation, but it gets a little more complicated when you start thinking about land surface cover. What's going on the surface of the Earth also affects the albedo of the surface of the material, of the surface. That can be a natural process. Like, for example, I have this satellite image of Africa, where they are showing, this is somewhat artificial how this was done. It's a composite over lots of days when the satellite was looking down and seeing where it was clear. This is one single day that was no clouds over Africa. But see how there's all these jungles and savannas and so on, and then farther to the north we have the Sahara? The jungles and the savanna have very low albedo. The desert has a very high albedo. Why would the jungles and the savanna have a low albedo? Because that's what plants do. Plants are in the business of absorbing shortwave radiation from the sun. They don't let that shortwave radiation get away. That's what leaves do. They absorb shortwave radiation to make their food. On the other hand, the desert is just sand and rock, and it might be much better at reflecting radiation. Now, you can see, here's my little trick for figuring out the albedo. Look if we switch to a black and white picture of the same thing. Okay, see how all that green area now looks really dark? Because actually very little shortwave radiation is being reflected by those surfaces. On the other hand, see how the Sahara is very bright? Because the sandy surfaces are mostly reflecting shortwave radiation. Now, you might be thinking, wait a minute, it's a Sahara Desert, it's hot, but almost all the shortwave radiation is being reflected. How did that happen? Oh, that's a complicated story. We probably can't get to that point in ATS 105. Stick with some atmospheric science classes like 113 or tropical meteorology, which only has ATS 113 as a prerequisite, and we'll teach you all about how deserts work. Okay, but we can see, hey, this natural difference in the land use makes a huge difference to the albedo. But it doesn't have to be natural. It could be man-made. Look at these center pivot irrigation fields out in the middle of some desert someplace. And see how we have this relatively light-colored surface that was the natural surface. This is probably bare soils and maybe some dry vegetation and so on that has a very high albedo. It's mostly reflecting shortwave radiation that hits it. And then these incredibly dark fields. Again, if I switch to the black and white view, it becomes very clear that the fields have a very different albedo than the sand around them. They're going to be absorbing shortwave radiation in a very different way than the desert around them is doing. Oh, man, we're going to have to keep track of a whole lot of things if we're going to understand how much shortwave radiation from the sun is being reflected by the surface of the Earth. We're going to have to know a lot about the albedo of the surface of the Earth and what that albedo means for how much radiation is being reflected. Okay, we can do that. Now, what about the atmosphere? There's radiation going every which way through the Earth's atmosphere, right? Radiation from the sun is headed down towards the surface of the Earth, except for some of the radiation from the sun is being reflected off the surface of the Earth and heading back up through the atmosphere. Some of it's being reflected off the clouds and headed back up through the atmosphere. Long-wave radiation from the ground is headed up through the atmosphere. Things in the atmosphere like clouds and dust and greenhouse gases and so on are all emitting radiation. Oh my word. The radiation, the atmosphere is like a crazy traffic jam of radiation. Everything that we've talked about so far with regard to radiation had a surface. The surface of the Earth, the surface of the food in your microwave, whatever. All these objects had a surface, and we sort of was saying that it was the surface of these objects that was doing the absorption or the reflection or the whatever of the radiation. And that's in general true to an object that has a surface. The surface of the Earth is what's emitting the long-wave radiation upward. The surface of the ocean is emitting long-wave radiation. Whatever. But the atmosphere doesn't really have a surface, okay? The atmosphere is just gases, and, you know, if you're talking about, like, solar radiation coming from interplanetary space, well, it starts hitting the very top of the atmosphere where there's a few molecules, and it starts out very thin, and then the atmosphere, as the radiation penetrates farther and farther into the atmosphere, it's hitting thicker and thicker gases. As the atmosphere gets denser and denser, the farther in you go. That's very different than hitting a surface. I mean, even if the monochromatic absorptivity of those gases is pretty good and pretty high, a given photon of radiation from the sun probably can make it some distance through the atmosphere, just because those top layers of the atmosphere aren't very thick. The likelihood that it hit any air molecules up high isn't all that good. So it's, even if those air molecules are good at absorbing that radiation, there just aren't very many of them. That photon of radiation at that wavelength probably can get pretty far in. On the other hand, how about radiation being emitted down at the surface of the Earth headed up? Down there, the atmosphere is thick and gooey. If the atmosphere is good at absorbing that kind of radiation, down there, there's a whole lot of molecules. Oh, so that radiation probably can't get very far away before it gets absorbed. So what actually happens to radiation as it tries to move through the Earth's atmosphere? Well, rather than talking generically about shortwave radiation, let's spend a moment or two on ultraviolet radiation, UV radiation. That's a type of shortwave radiation. It has a shorter wavelength than visible light. You might remember ultraviolet radiation is the type of radiation that does things like cause skin damage and skin cancer. It's bad stuff. Now, as it happens, we have a gas in the Earth's atmosphere called ozone that is really, really astonishingly good at absorbing ultraviolet radiation. It has very high absorptivity. Now, most of the Earth's ozone, to a good approximation, let's say, is in the so-called ozone layer, which I'm showing here as like a yellow shield or something over the surface of the Earth. Okay. Up high in the Earth's atmosphere, at about 25 kilometers up, there's a layer of the atmosphere that has a lot of ozone in it, called the ozone layer. And when photons of ultraviolet radiation come from the sun and start encountering the Earth's atmosphere, well, way up high in the atmosphere, 50, 75, 100 kilometers up, those molecules that are up there are generally not ozone. The molecules that are up there are generally not gases that are very good at absorbing ultraviolet radiation. Their monochromatic absorptivity for the wavelengths associated with ultraviolet radiation, their absorptivity is not that high. Let's say 0.2. Okay? Those molecules don't really absorb all that much ultraviolet radiation, and there aren't very many molecules up there. So actually, most of the ultraviolet radiation from the sun doesn't have any trouble getting through the upper part of the atmosphere. But then it encounters the ozone layer. Now, once it starts encountering the ozone layer, at that layer, every cubic meter of the air has a lot of ozone molecules in them, and ozone molecules have a very high absorptivity, close to 1 for ultraviolet radiation. And so, yes, some photons of ultraviolet radiation get a little ways through the ozone layer, and some photons of ultraviolet radiation barely get anywhere before they just have bad luck and they hit an ozone molecule. Some make it farther, some make it less far. Yeah, once in a while a photon does get through. I mean, that's why you get sunburns, that's why people get skin cancer, is because some photons do manage to get through. They just get lucky. An individual photon managed to get through the whole ozone layer without hitting a single ozone molecule. That happens. But the vast, vast majority of them don't. But see how there was sort of we had to take into account how thick the gases were, how good they were at absorbing radiation at those wavelengths? That's a complicated problem. We can do the same sort of a story with long-wave radiation. Here I have the surface of the Earth emitting long-wave radiation upward through the atmosphere up towards interplanetary space. Now down here at the surface, the atmosphere is thick and gooey, right? The density of the atmosphere is very high. Every cubic meter of the atmosphere down here into the surface of the Earth has a really large number of molecules. Some of those molecules are greenhouse gases, and so they're pretty darn good at absorbing long-wave radiation. Now the surface of the Earth is emitting long-wave radiation at a range of wavelengths. Some of it's infrared, some of it's microwave, some of it's even radio wave, although not much radio wave. Even within infrared, there's a range of wavelengths that can emit, and so on. And some of that radiation happens to be at wavelengths that the Earth's atmosphere is not that good at absorbing. And so that radiation makes it right past all those molecules, even though the atmosphere is thick and gooey down there at the surface. Some of that long-wave radiation does make it all the way out to space. No problem. But most of it doesn't. Most of that long-wave radiation that the surface of the Earth is emitting pretty quickly hits something that's good at absorbing it, because there's just a whole lot of molecules down low in the Earth's atmosphere. If some greenhouse gas like carbon dioxide or methane or whatever, is in the way, that photon of long-wave radiation gets absorbed. Maybe it's just a few meters above the surface of the Earth, maybe it's a few kilometers above the surface of the Earth, but the majority of it's going to get absorbed before it gets away. Oh. So once again, we're going to have a complicated issue here of where you have to think about how much of the gases there are, and how many molecules there are of these gases that are good at absorbing radiation, and how good are they at absorbing the radiation, before we're going to be able to figure out how much radiation can get away and what happens to the radiation that gets absorbed and so on. Some radiation is going to make it through the atmosphere, some is not. Some radiation is going to make it way far through the atmosphere before it gets absorbed. Some of it will barely get any distance before it's absorbed. This is going to be a lot to think about. Yeah, you know what? Actually, it's a great equation. I'm not going to show you the equation because it's got some scary mathematical symbols in it, but it's called Beer's Law. Yeah, as in beer. Beer's Law explains all of this. We're going to be talking about how that all works in our next lecture, where we're going to be talking about the energy balance of the Earth. How do we balance the amount of radiation that we're getting from the sun with the total amount of radiation that we are giving off in all directions by long-wave radiation? That's the next lecture. Before we go on to the next lecture, I want to ask you a couple more questions. Question 3 is another idea about like a climate context to our understanding about these radiation properties and so on. A volcano. A volcano spreads dark soot all over some Antarctic ice sheet. This blank the albedo of the ice sheet. Does this increase the albedo or does this decrease the low albedo of that surface? Take a look at your two options, follow one of the two links below this video to get some feedback about your answer.